What if everything we thought we knew about the origin of life on Earth was wrong? What if, instead of bubbling out of some warm little pond in a prehistoric Earth, life came from out there? Not metaphorically, literally. What if we aren't the product of this planet, but the descendants of something older, stranger, and far more universal, seeds of life riding through the void, silently drifting across galaxies, waiting to fall onto a world like ours? It sounds like science fiction, the plot of some cosmic thriller, but it's not. It's a scientific hypothesis, and it has a name: Panspermia. Panspermia isn't new. The idea dates back to the ancient Greeks. But in the 21st century, with everything we've learned about biology, chemistry, and the extremities of space, it's starting to feel plausible. Disturbingly plausible. Because here's the thing, the deeper we look into the origins of life, the more we realize something unsettling. Life on Earth appeared fast, shockingly fast, too fast. The Earth cooled enough to support water about 4.4 billion years ago, and by 4.2 billion, we already have signs of life. Not just some molecules randomly dancing, actual cells. Primitive, yes, but organized, breathing, reproducing, alive. That's a blink in geological time, barely enough time to finish forming the crust, let alone cook up life from scratch. So the question becomes, did it really start here or did it arrive here? That's where panspermia comes in. It suggests that the first ingredients for life, or life itself, came from space, delivered to Earth on comets, asteroids, or microscopic dust particles. And while it sounds outrageous, there's one thing: it's not impossible. In fact, it's alarmingly feasible, because we now know that some organisms, like tardigrades, those microscopic, water-loving, chunky space bears, can survive in the vacuum of space, not for minutes, for years. They can endure cosmic radiation, freezing temperatures, dehydration, and still come back to life like nothing happened. In other words, if they hitched a ride on a rock, hurtling through space, and crash-landed on a wet, warm Earth, they might walk away from it, or rather, crawl. But it's not just about tiny animals. Meteorites that have landed on Earth, like the Murchison meteorite in Australia, are teeming with complex organic molecules, sugars, amino acids, even the building blocks of RNA. Some of these compounds aren't even native to Earth. They're extraterrestrial, formed in the icy depths of space and delivered like a galactic care package, which raises the unsettling thought: what if Earth is just the recipient of a delivery? A place where life, seeded from far away, found a perfect environment to thrive. As we begin this story, you need to understand, this isn't just about science. This is about perspective, identity, destiny. If panspermia is true, it means we are not alone in the sense that we've never been alone. We are part of something larger. A chain reaction spanning solar systems. Life might not be the exception. It might be the pattern. And Earth, just one chapter in a cosmic autobiography still being written. Life, by all logical accounts, shouldn't have shown up so quickly. Earth was forged in fire, a violent, molten world bombarded constantly by meteors, ravaged by radiation, scorched by a sun still settling into stability. For hundreds of millions of years, our planet was less a home and more a hazard. Oceans had not yet fully formed. The crust had barely solidified. Volcanoes erupted without pause. The atmosphere was a chaotic mix of noxious gases, lightning, and ash. In short, it was hell, and yet, somehow, life appeared. Not eventually, not after eons of chemical trial and error, but fast. Too fast. We know this from ancient rocks, some over 4 billion years old, that carry chemical fingerprints of life, isotopic ratios, microfossils, and structures that could only be produced by biological processes. These signs aren't vague suggestions. They're persistent, recurring, and increasingly difficult to dismiss. They tell a story of a world that cooled just enough to form water, and almost immediately, life grabbed hold, like it had been waiting, like it was ready, like it came prepared. Think about that. The Earth becomes marginally habitable, and boom, life. Not just basic chemistry, but organized, replicating life. RNA strands forming, cells dividing, tiny biochemical engines switching on. The last universal common ancestor, Luca, wasn't a lonely accident. It was already a complex entity, not something you'd expect to crawl out of a chemical soup after just a few million years. And that's the problem. Because origin of life chemistry is slow, painfully slow. Experiments in labs today still can't fully replicate how non-living molecules turned into living systems. We can build precursors, pieces, but the full leap, the spark, it's still elusive. So how do we explain the speed? Either we're missing something enormous in our understanding of chemistry, or Earth had a head start. A seed, a spark from elsewhere, because if life began somewhere else, on another planet, or a moon, or even within a nebula, and found its way here, then that speed makes more sense. Earth didn't invent life, it inherited it. Panspermia doesn't answer every question, but it reframes the timeline. It shifts the burden of proof. Life didn't originate on Earth, it arrived ready to bloom. And that's where this gets even more provocative. Because if life can start elsewhere and move, if it can survive the cold of space and the impact of landing, then Earth may not be unique at all. We may just be one of many. Life may be a contagion spreading from world to world, galaxy to galaxy, wherever the conditions allow. It's no longer about how rare life is, it's about how durable and resilient it might be. The speed of life's appearance on Earth is not just a footnote, it's a clue. A crack in the foundation of our Earth-centric view of biology. It suggests that maybe the most important story we've ever told, the story of how we came to be, didn't start here at all. It began out there, in the stars, and Earth was simply the first place it found a warm welcome. To believe in panspermia is to believe that life can survive the unimaginable, the vacuum of space, the radiation of stars, the freezing darkness between planets, and the violent impact of crashing onto a new world. At first glance, this seems like science fiction. How could any living thing endure such extremes? Isn't life fragile? Doesn't it require protection, warmth, oxygen, and food? That was the assumption for decades, until we met the extremophiles, until we met the tardigrades. Tardigrades, sometimes called water bears or moss piglets, are tiny microscopic creatures, no larger than a grain of salt. They're found everywhere, from mountaintops to the deepest ocean trenches, from Arctic ice to boiling springs. But what makes them remarkable isn't just their adaptability, it's their invincibility. When faced with extreme environments, they enter a state called cryptobiosis, a kind of suspended animation where metabolism all but stops. In this state, they dry out, curl up, and effectively shut down all biological activity. And like this, they can survive almost anything. In 2007, scientists launched tardigrades into low Earth orbit, exposing them to the vacuum of space, intense cosmic radiation, and the full fury of solar UV rays. No suits, no shielding, just the raw, brutal environment of outer space. And when they were brought back to Earth, they rehydrated and walked away. Not all of them, but enough to make headlines. Enough to make scientists rethink the boundaries of survivability. This was not theoretical. This was real biological proof that life can endure conditions previously thought to be instantly lethal. But it's not just tardigrades. Other extremophiles, bacteria like Deinococcus radiodurans, which can survive 1,000 times the radiation dose lethal to humans, or archaea that thrive in boiling acid pools, show us that life isn't just adaptable, it's relentless. These organisms have been found living inside nuclear reactors, beneath Antarctic ice sheets, and in salt crystals over 50 million years old. They defy expectations and remind us that life's requirements are broader and stranger than we once believed. So, what happens when we take that knowledge and look to space? Suddenly, panspermia doesn't feel so far-fetched. If a microbe or dormant organism like a tardigrade hitched a ride inside a rock, ejected by a massive impact, say from an asteroid collision, it could, in theory, survive the journey. Encased in stone, shielded from radiation, frozen in cryptobiosis, it could drift for thousands, even millions of years. And if that rock were to land on another planet, one with warmth, water and the right conditions, that life could wake up, restart, multiply, colonize, not as an invader, but as a pioneer. It's a cosmic delivery system that doesn't need spaceships or propulsion, just time, just luck, just the astonishing resilience of life itself. And in that resilience, we find the first building block of belief in panspermia. Because if something as small as a tardigrade can survive the void, maybe life is more portable than we thought. Maybe the universe isn't empty between stars. Maybe it's teeming with dormant seeds, just waiting for the right place to bloom. When we imagine meteorites striking Earth, we often picture destruction, giant impacts, extinction events, craters gouged into the crust. But not all rocks from space come to end life. Some may bring the raw ingredients to start it. For billions of years, Earth has been bombarded by debris from the solar system. Asteroids, comets, and space dust carrying the chemical building blocks of life. And while this might sound poetic or speculative, it's backed by hard evidence embedded in the stones that have fallen from the sky. Take the Murchison meteorite, for example. It crashed into Australia in 1969 and has since become one of the most studied space rocks in history. Scientists found something extraordinary in it, over 70 different amino acids, the very molecules that make up proteins, the essential machinery of life. Even more remarkably, some of these amino acids are rare or non-existent on Earth. They aren't contamination, they're alien, formed in the cold reaches of space, likely in interstellar clouds or early solar system material. They show that organic chemistry isn't confined to our planet. It's happening out there all the time. But amino acids aren't the only surprise. In recent years, researchers have detected sugars like ribose, the backbone of RNA in meteorites. This is monumental. RNA is thought by many scientists to be the precursor to DNA, a more primitive and flexible genetic material capable of storing information and catalyzing chemical reactions. If meteorites are carrying ribose to young planets, they're essentially delivering the core components needed for the origin of life. Not metaphorically, literally. They're sprinkling planets with biochemistry. What's even more fascinating is that these compounds are stable enough to survive the heat and shock of atmospheric entry. When a meteorite barrels into Earth, it generates extreme friction, reaching thousands of degrees. But inside, the core can remain cool, shielded from the inferno outside. This natural insulation allows complex molecules to make the journey intact. Over millions of years, these deliveries add up, billions of tons of space material raining down on Earth, not just as inert rock, but as organic cargo. This phenomenon isn't limited to the past. Even today, space dust is constantly falling onto Earth. an estimated 5 to 300 tons every single day. Tiny particles too small to burn up settle quietly on our planet unnoticed. And some of these particles, especially those from comets and carbonaceous chondrites, carry organic compounds. The universe, it seems, is not stingy with the ingredients for life. It's generous, prolific, overflowing. The implications are profound. If Earth received its first spark of life, or at least its vital molecules, from above, then our story is part of something much larger. We didn't begin as an isolated experiment. We were part of a grander chemical exchange happening throughout the cosmos. A cosmic soup where the recipe for life isn't guarded by one planet, but written into the very dust between the stars. Panspermia doesn't require us to imagine alien spacecraft or directed interventions. It invites us to look at the sky, to realize that the seeds of life might drift through the cosmos like pollen on the wind, settling, waiting, blooming when they find the right soil. And sometimes that soil is a young, chaotic planet called Earth. Speculation becomes science the moment it touches experimentation, and few ideas have teetered so long between wonder and skepticism as panspermia. For years, it remained a tantalizing concept. Possible, perhaps, but impossible to prove. But that changed with one mission. Tampopo, named after the Japanese word for dandelion, a plant whose seeds drift in the wind. Tampopo was a bold experiment by JAXA, the Japan Aerospace Exploration Agency, to test whether life, or the building blocks of life, could survive and travel through space, not just in theory, but in practice. The stage, low Earth orbit; the laboratory, the exterior of the International Space Station. Launched in 2015, Tampopo set out to answer two fundamental questions. First, could life survive in the vacuum of space for extended periods of time? And second, are organic particles, possibly even microbes, actually moving through the solar system, riding on dust and meteorites? To investigate this, scientists mounted tiny plates on the outside of the ISS. These plates were coated with bacteria, spores, amino acids, and other organic compounds. Some samples were shielded from ultraviolet radiation, others were fully exposed. All were left in the harshness of space. No atmosphere, extreme temperature swings, and full bombardment by solar and cosmic radiation. And then, after 1 year, 2 years, and even 3 years, the plates were brought back to Earth. The results were astounding. Many of the bacteria, particularly those clustered in dense aggregates, had survived. Not just fragments of DNA, actual viable organisms. The shielded samples fared better, of course, but even some exposed ones showed remarkable resilience. Even more incredible was the survival of amino acids and other organic molecules. Despite constant UV exposure, some still retained their structure. These molecules, if hidden in crevices of meteorites or within dust particles, could feasibly make the journey between planets. But Tampopo didn't just test whether life could survive space. It also tried to catch it. Using ultra-clean aerogel panels, the experiment aimed to collect cosmic dust and micrometeorites from the vastness around the ISS. When the panels were returned and analyzed under microscopes, they revealed particles with unique signatures, carbon-rich, porous grains consistent with interstellar origin. While no confirmed alien microbes were found, the very act of collecting extraterrestrial dust and analyzing its organic content brought panspermia from the pages of theoretical biology to the front lines of experimental science. What Tampopo proved unequivocally is that the conditions of space, while harsh, are not insurmountable. Life, especially in dormant forms, can endure them. Organic molecules can persist, through cosmic exposure, and tiny particles are indeed floating between planets, potentially carrying the seeds of life across unimaginable distances. We no longer have to ask if it's possible for life to travel between worlds. The answer is yes. It's not easy, and it's not frequent, but it is entirely within the realm of the real. In this sense, Tampopo didn't just scatter the seeds of theory, it planted the roots of evidence. It showed us that space is not sterile, it is not empty, it is, in fact, a vast highway where microscopic life might quietly drift, invisible to the naked eye, waiting for gravity and chance to deliver it to a new home. And when that home is warm, wet, and welcoming, like Earth once was, life might take hold. Again, at first glance, panspermia might seem like just another fringe theory, a cosmic curiosity best left to speculative science fiction. But the more seriously we examine it, the more we begin to understand that this idea carries weight far beyond biology or astronomy. It doesn't just attempt to explain how life may have arrived on Earth. It challenges the very core of how we define ourselves, our place in the universe, and our assumptions about life's rarity. The panspermia hypothesis matters because it rewrites the story of life, not just Earth's story, but potentially the entire universe's. Let's start with perspective. For centuries, humanity has thought of life as a local phenomenon. Earth was the cradle, the only known planet teeming with biology, the only oasis in a sea of lifelessness. And so, naturally, we assumed life originated here, sprouting slowly from a primordial soup, driven by chance chemical reactions and favorable conditions. But panspermia flips that narrative on its head. It suggests that Earth may not be the origin, but merely one stop in a much longer chain. Life, under this lens, becomes something not tied to one world, but something that moves between them. An interplanetary traveler, a phenomenon as universal as gravity or starlight. That shift in perspective changes everything. Because if life didn't begin here, then we have to seriously consider where it did begin. Was it Mars, back when it had rivers and lakes? Was it a moon like Europa, or Titan, or Enceladus? Was it a place that no longer exists, destroyed in some ancient cataclysm? Or did it begin even further away, in another star system, billions of years before Earth even formed? Panspermia opens that door. It says that life may be older than our planet, perhaps older than our solar system, and if that's true, then life might be everywhere. Not just Earth-like life, but microbial life, dormant life, alien life, waiting for the right environment to awaken again. Beyond the science, panspermia matters because it forces us to ask deeper questions. If life is that durable, that mobile, that resilient, then what does it mean to be unique? Are we truly alone, or just the latest branch of a much larger biological family tree, one whose roots stretch across galaxies? And if other worlds have been seeded too, then life elsewhere isn't just possible. It's likely that possibility reframes our approach to exploration. Mars missions, Europa probes, even telescopes studying distant exoplanets. They're no longer just searching for the improbable, they're hunting for relatives. Culturally, the idea is equally profound. Most myths and religions treat life, especially human life, as special, chosen, or divinely crafted in one sacred place. Panspermia doesn't invalidate those beliefs, but it challenges the geographic assumption. What if the divine spark came from the stars? What if life is meant to spread, to endure, to migrate, like stardust seeking new soil? It reframes purpose itself. It turns us from earthlings into citizens of the cosmos. And perhaps, in the grand scheme of things, that's what we've always been. So, yes, panspermia matters. Not because it's conclusive or proven or beyond doubt, but because it dares to expand our imagination with scientific plausibility. It invites us to look up at the night sky, not as a black void, but as a highway of possibility, one where life is not the exception, but the rule. And if life is indeed seeded across the stars, then we, the people of Earth, are not the beginning of the story, merely the continuation. If panspermia is more than just a thought experiment, if it's a genuine mechanism for life's propagation across the universe, then the question is no longer just, did life come from space, but where else has it gone? That shift in focus has a profound impact on how we approach the exploration of our solar system and beyond. It changes what we look for, where we look, and even how we conduct ourselves as we reach out into space. Because if life has been seeded throughout the cosmos, if planets and moons are potential incubators, not barren rocks, then we may be stepping into living worlds without even realizing it. Let's begin with Mars, the most obvious and immediate candidate. Once home to liquid water, a thick atmosphere, and possibly even oceans, Mars may have been Earth-like billions of years ago. It also shares a unique geological link with our planet. We've found Martian meteorites on Earth, ejected from Mars long ago by asteroid impacts. These rocks carry with them not only minerals, but traces of organic compounds, and perhaps, at some point, microbial passengers. If panspermia is true, Mars may have been both a sender and receiver in this interplanetary exchange. So when we send rovers to dig, drill, and scoop Martian soil, we're not just searching for Martian life. We might be tracing our own origin story. The same goes for Europa and Enceladus, icy moons with vast subsurface oceans, heated by tidal forces and laced with complex chemistry. Plumes of water vapor erupting from their surfaces offer glimpses into environments that may harbor not just life, but a whole hidden ecosystem. And if life evolved there, it may not be entirely native. It could be seeded by comet dust, meteorite impacts, or ancient material drifting through space and settling into warm, welcoming habitats. This brings us to a critical consideration: planetary protection. If the universe is fertile, then our probes, landers and rovers become not just explorers, but potential contaminants. We risk seeding other planets, not with alien life, but with Earth's own microbes. Tiny stowaways hidden in corners of spacecraft, resistant to radiation and desiccation. Ironically, we could end up triggering panspermia ourselves, not by accident of the cosmos, but through the deliberate act of exploration. The ethics of this are enormous. Do we have the right to alter untouched ecosystems, even if they're microbial? Should we be caretakers of planetary integrity or ambassadors of earthly biology? But beyond the risk lies opportunity. Understanding panspermia could help us identify new biosignatures, traces of life detectable in distant atmospheres, mineral structures, or isotopic ratios. It could redefine what a habitable zone really means, no longer just the Goldilocks band around a star, but any environment where organic chemistry can persist, even for short spans. If life travels, then even rogue planets, those drifting in darkness, might bear its fingerprints. Our telescopes, satellites, and future missions may soon turn up evidence that life is more common than we imagined. And if that happens, the question shifts from "are we alone?" to "how many versions of us are out there?" Perhaps life doesn't just endure against the odds. Perhaps it's part of the architecture of the universe itself, designed not only to survive, but to spread, to seek, to awaken wherever the conditions allow. In embracing panspermia as a scientific framework, not just a wild idea, we don't just expand our theories, we expand our responsibilities, our curiosity, and our hope. The universe might not just be a backdrop for life, it might be its cradle, its crucible, its carrier, and we might be walking in the footsteps of something ancient, carried across time and space, ready to begin again. Panspermia is seductive. It appeals to our cosmic imagination, offering a sweeping, almost poetic explanation for the origin and spread of life. But in science, beauty is not enough. A theory must not only inspire, it must withstand scrutiny. And make no mistake, the panspermia hypothesis, though compelling, is far from universally accepted. In fact, it resides at the edges of mainstream science, often embraced with cautious intrigue, but rarely with full conviction. The reasons are not born of closed-mindedness, but of hard, sober skepticism, a skepticism rooted in evidence, or rather the lack of it. Perhaps the most common objection is that panspermia doesn't actually explain the origin of life, it just relocates it. If life came to Earth from somewhere else, then how did it begin there? Shifting the question to another planet or solar system doesn't solve the fundamental mystery of abiogenesis, the transformation of non-living molecules into self-replicating systems. It's like answering the riddle of the chicken and the egg by saying the egg came from another farm. Scientists want answers, not deferrals. Until we understand how life begins, relocating where it begins feels unsatisfying to many researchers. It's seen as philosophical outsourcing. Another valid criticism is the lack of direct evidence. For all the amino acids in meteorites, for all the microbes surviving in space, we have yet to find a truly extraterrestrial life form. Every living thing we know shares the same biochemistry: DNA, RNA, proteins built from the same 20 amino acids, all operating under the same genetic code. If life was seeded from multiple origins, especially across vast cosmic distances, why don't we see more biochemical diversity? Why is everything so uniform? This uniformity suggests a single origin point, perhaps Earth itself. Without alien biochemistry to compare, panspermia remains a hypothesis in need of a smoking gun. The mechanics of panspermia also invite skepticism. While some extremophiles can survive space in laboratory conditions, it's another thing entirely to endure millions of years of cosmic radiation, vacuum and cold while drifting between star systems. Even with shielding, DNA degrades, membranes rupture, and entropy takes its toll. The probability of a viable organism surviving such a journey, let alone arriving intact and able to reproduce, is exceedingly small. It's not impossible, but critics argue that improbable events demand extraordinary evidence. So far, that evidence is circumstantial. There's also concern over motivation. Some see panspermia as an intellectual shortcut, a way for scientists to dodge the hard work of uncovering abiogenesis on Earth by shifting the burden elsewhere. It's viewed by some as a form of defeatism dressed as wonder. Why propose interstellar travel for microbes when we still don't fully understand hydrothermal vents, tidal pools, and early Earth chemistry? Better, they argue, to look inward, to our own planet's early conditions before gazing outward. And yet, skepticism is not dismissal. The scientific community doesn't reject panspermia out of disdain. It demands better proof, tighter models, and empirical data that rise above speculation. That's how science works. The theory must be stress-tested, doubted, and refined. For panspermia to move from possibility to probability, it must clear higher bars than mere plausibility. It must show not just that life can travel between worlds, but that it did. Until then, panspermia exists in a liminal space, too reasonable to ignore, too unproven to embrace. It stirs minds, sparks debate, and pushes the boundaries of what we think life can do. But like all great scientific ideas, it must survive its critics, not by silencing them, but by answering them. Panspermia is more than a scientific hypothesis. It is a profound shift in how we think about life, origin, and connection. It asks us to stop seeing life as a miracle confined to a single world, and begin imagining it as a thread woven through the fabric of the universe itself. In doing so, it repositions humanity not as a unique fluke in the cosmic silence, but as a chapter in a much older, much broader biological epic, one that may have started billions of years before Earth ever formed. The theory does not reject the wonder of life on Earth. Instead, it magnifies it. It takes our story and stretches it across the stars. In the centuries-old search for where we come from, humanity has looked to gods, chemicals, and randomness. Panspermia offers a different kind of answer, not rooted in mythology, not limited by terrestrial chemistry, but suspended somewhere in between, grounded in biology, astrophysics, and the stubborn resilience of life itself. It tells us that microbes might travel across planets embedded in rocks, that DNA might hitchhike on comets, that even now, as we speak, organic dust may be drifting through space, like pollen seeking a flower. It reframes Earth not as the birthplace of life, but as one of many gardens where life can take root. And in doing so, it forces us to ask, how many other gardens are there? But perhaps the most powerful aspect of panspermia isn't just what it suggests about the past. It's what it implies about the future. If life can survive interplanetary and even interstellar journeys, then so can we. Not today, maybe not even this century, but eventually the same forces that may have carried microbes between worlds could someday carry us. Humanity could become a continuation of that biological journey, not only seeded by the stars, but destined to return to them. We are not foreign to the cosmos. We are its offspring. And yet, we must be cautious. The story of panspermia is not yet complete. It is filled with maybes, hypotheses, and tantalizing evidence that flirts with certainty but never quite arrives. Skeptics rightly point to the need for proof, real, incontrovertible proof, that life exists elsewhere or that it can survive for eons in the depths of space. But as our technology advances, as our telescopes grow sharper and our missions more daring, the evidence may come, perhaps from a Martian microbe dormant beneath red dust, perhaps from Europa's icy ocean, perhaps from the spectral signature of biology on a faraway exoplanet. And when that moment comes, it will not be the discovery of an alien. It will be the confirmation of kinship. Until then, panspermia remains one of the boldest, most imaginative frameworks through which we can view the mystery of life. Not just because it might be true, but because it dares us to dream beyond boundaries planetary, biological, and intellectual. It tells us that life does not belong to Earth alone. It belongs to the universe. And in that vision, we find a rare kind of hope. Not just that we are not alone, but that we were never meant to be. Life, it seems, is not the exception. It is the pattern, and we, drifting here on our pale blue dot, are part of something ancient, enduring, and beautifully cosmic.